Team 8's interim project movie. We are designing an electric scooter. For our system summary, the chosen system for this project is an electric scooter. The scooter must meet performance requirements, including minimum cruising speed, acceleration capability, and structural safety, while maximizing the driving range under constraints of system mass, cost, and component efficiency. The three subsystems we are analyzing are the battery subsystem, the motor subsystem, and the frame subsystem.
As for the system block diagram, we have three subsystems, the battery, motor, and the frame. For the battery, we have battery mass and range as an output. For the motor, top speed, required power, motor mass as an output. As for the frame, we have drag and frame mass as our output.
Looking at some of our shared parameters and coupled variables between the three subsystems, the two main parameters that all the subsystems share are rolling resistance and rider mass, assuming max rider mass. Variables that link our subsystems include the mass of the battery, the mass of the motor, and the mass of the frame, as well as top speed, required power, and aerodynamic drag.
To solve our optimization problems, we use the interior point algorithm implemented in MATLAB's fmincon function.
For the battery subsystem, our design variables are the battery weight and the gravimetric efficiency of the battery. The constraints we put on the subsystem are the side constraints on the mass and gravimetric efficiency, and we have the cost of the battery restricted to being less than or equal to $200. The objective function is to maximize the range that the battery provides. For the mathematical model of the battery subsystem, we have two major outputs, the battery range and the battery cost. And maximizing that battery capacity is going to increase our available energy for the scooter and improve our range. As for assumptions, we're assuming that the battery technology is lithium ion, and we're modeling the cost using data, which is just the cost versus the gravimetric efficiency. And the range is being calculated assuming a constant velocity and power as a simple subsystem model for the battery.
This slide summarizes the optimization results for the battery subsystem. As you can see, we tested several different initial guesses, and no matter what, they all consistently converge to the same final design solution, which indicates that the solution lies within a well-defined optimal region. The optimization selected the maximum allowable battery mass, 10 kilograms, indicating that the higher mass most directly increases achievable battery capacity within the constraints more effectively than gravimetric efficiency. The optimal gravimetric energy density was approximately 119 watt-hours per kilogram, which maximizes range while satisfying the cost constraint, and the resulting range is about 10 kilometers, which represents the maximum range capability within the simple subsystem optimization.
For the motor subsystem, we had two design variables, which were system max speed and system acceleration. Some of the constraints we included were that our max speed should be over 25 kilometers per hour. The acceleration should be over 5 kilometers per hour per second. But the mass of the motor should be less than or equal to 10 kilograms, and that the overall cost of the motor should be less than or equal to $120. Our main objective function is to minimize the motor power requirement, minimizing the rolling resistance and aerodynamic drag while still being able to maximize speed and acceleration. For the motor power calculation, our main modeling approach was to minimize overall power, which would therefore minimize motor mass while maximizing speed and acceleration. We also included the cost of the motor that would be subject to the power of the motor multiplied by cost per motor power. Some of our assumptions included that the coefficient of friction and the drag coefficient would remain constant. We also assumed that the total mass used has already been optimized by other subsystems, and that our rider position is fixed during the operation of the scooter.
We selected for our initial guesses several points within the acceptable range for our constraints. Overall, the optimization converged to a minimum speed acceleration and resulted in an F-star value, our power required. So the optimized motor design corresponds to a motor that can supply 8.6 kilowatts of power with a maximum speed of 25 kilometers per hour and a maximum acceleration of 5 kilometers per hour per second.
For the frame subsystem, we chose the two variables, frame length and the frame width. The constraints basically are limited by 0.8 meters for the length and lower than 1.2 meters. For the width, our bounds are 0.2 meters and 0.4. The structural stress, our frame should be less than the yield stress of the aluminum, and the mass frames have to be less than 10 kilograms. The cost of the frame also have to be less than $100, and the cruising speed is 25 kilometers per hour. The objective function is to minimize both friction and aerodynamic drag. For the modeling approach, we have two major outputs. The first one is the friction force, that is the mass that must be minimized in order to minimize the friction force. And the second one is the aerodynamic drag. Here, the aerodynamic drag must be also minimized to minimize the overall force that the motor must overcome to move forward, requiring less power and increasing the range. And the cost of the frame will be subject of mass of aluminum multiplied by the cost of aluminum. Here we got some assumptions. Basically, the frame material is homogeneous. The aerodynamic drag coefficient remains constant. The frame behaves as a simple solid beam structure, and the position of the rider is in the center of the frame.
The optimization consistently converges for the frame length of 0.8 meters, the width 0.2 meters, and therefore overall overcoming force of 27.6 newtons. As for our results, the optimized frame design corresponds to a shorter frame length, reducing the structural mass, the width of 0.2 meters, minimizing aerodynamic drag. These results indicate that lightweight frame design and aerodynamic efficiency are critical factors for improving electric scooter range. As for a conclusion for electric scooter subsystems, we have battery subsystem and motor subsystem, frame subsystem results showing here. And that concludes our presentation. Thank you.